Hello everybody, today we're going to cover chapter 2 topics. Most of this should be a somewhat of a review because a lot of this is the AC fundamentals class that we took previously, but it's important to go over it to kind of make sure everybody's fresh on it because a lot of these concepts are used in RF electronics, particularly reactive elements like capacitors and inductors and things like that. We're also going to cover decibels, some gain, and attenuation. These tuned circuits, we're going to be doing one of those in our lab this week, the RLC circuit, and then we'll finish up with Fourier theory. Sometimes I start with Fourier theory, but that's not how this presentation is set up. So the reason I would start with it is because Fourier theory is super important. I might actually go over it again when we're the next time, because it is super important to understand that. It's fundamental to a lot of different things that we encounter in high-speed circuits. So first of all, we're going to talk about gain, attenuation, decibels. In all electronic circuits, we attenuate signals and we add gain to signals and things like that to get them where they need to be. Sometimes we actually do multiplication and division, sometimes integration, and sometimes we do differentiation. Sorry about that. So amplification, we use an amplifier, obviously, and the gain is V out over V in. Now this is a linear gain. This is not dBs or logarithmic that we'll talk about in a minute. But gain is simply output voltage over input voltage. That's for voltage gain. That's what the little v is here under AV. Sometimes it's current gain, in which case it'd be output current over input current. Sometimes it's power gain, in which case it's output power over input power. When we talk about power gain, a lot of times we'll use the decibels expression instead of this linear expression here. And here's power gain, as I mentioned, power out over power in. So here's a little example. 6 watts gain is 80. So P in is going to be, if you rearrange this equation, it's 6 over 80. So it's 75 milliwatts is the input power in this equation. Power gain is used a lot in RF, more than voltage gain or current gain. Voltage gain is used a lot in audio. Power gain is mostly in RF. When you have two amplifiers or more cascaded together, if the expressions are in linear form, as we've been doing up to this point, meaning not dBs, you can just multiply them together. So if you have a gain of 5, 2, and 17, 5 times 2 times 17 is 170. With this example, we have 40 milliwatts on the input, so you get 6.8 watts on the output if you multiply that times 170. Understand that if it's in dBs, you would just add them instead of multiplying them. I think there's an example for that later. Now, attenuation is indeed when you actually lose gain, or it's a negative gain or fractional gain. So you actually lose signal. You lose signal amplitude. And that's important sometimes. Sometimes you need to attenuate signals. For example, the front end of an RF receiver, it can saturate very easily if the transmitter is very close. So you add some attenuation in there so that doesn't happen. Common attenuator is a voltage divider, and we're all familiar with this. R2 over R1 plus R2 times Vn is the output of this. If you don't want to do this calculation, it's not hard, but I often at work I'll use a voltage divider calculator. It'll calculate the resistors for me, and that's just Google voltage divider calculator, and it comes right up. It's very simple. There's a few of them out there, and they all work great. So it allows you to choose resistors in a convenient way. Here's an example of an overall system with a loss stage, a loss circuit, loss component. So notice the gains are fractional, 0.2, 0.9, 0.0, or less than 1, which means you lose signal. 3 volts in, what do you get out? 32.4 millivolts. So you just again multiply these all together. Now, decibels is what we use most often in RF to express attenuation and gain. It was originally created to express hearing response is logarithmic. Decibel is 1/10 of a bell. When we convert them into gain and attenuation in decibels, you can do the overall gain by adding the individual gains or attenuations expressed in decibels rather than multiplying them. So you add now because it's in decibels. So here's your decibel calculations. V out or V in, this is the linear expression we were talking about earlier. Take the log of that times 20, that's the dB equivalent. Current gain, same thing. Power gain, however, it's 10 log of P out over P in. And this is something I believe you covered in your AC circuits. We do a lot of this power gain in RF. So here's a voltage gain equation in dBs. So 5 volts divided by 3 millivolts, 20 log of that, you get 64.4 dB of gain. Okay, obviously it's gain. Now if this was the other way around, this would be a negative number. In other words, if it was 3 millivolts divided by 5, in other words attenuation, you would end up with a negative number here. Negative dBs, which means an attenuation. And here's an example of one of those. So output of 2 milliwatts, input 50 milliwatts, so 2 divided by 50, you get a negative number, about minus 14 dB. These examples are really important to take a close look at. The reason I say that is because on the exams, I do use a lot of examples as the problems. So if you study these, you'll be in good shape. Antilog is where you go the other way. It's 10 to the x, or so it's the opposite of log. Okay, and then decibels. If you reference the value to a milliwatt or the carrier, where the reference is the carrier power. We don't know what that is yet, probably, but the carrier is the actual signal you tune to on a receiver, or what the transmitter is transmitting frequency. Those would get a little extra letter here, dBm and dBc. So if you reference the power to a milliwatt, dBm is pretty common. We'll do some examples of that too. So this is something that you should do on your own. I don't believe we have an answer here, but we have 90 milliwatts across 10K. Output is 7.8 volts across 8 ohm speaker. What's the power gain in decibels? So I want you to do this on your own. This is an example out of the textbook. Remember, power is what? Voltage times current, or V squared over R, or I squared times R. So you have V and you have R, so on each one of these, so you're going to do V squared over R. V squared over R on the output, V squared over R on the input. So output over input. That's the power gain. You'll get it. Remember, it's 10 log of that. So here's tuned circuits, our second topic. Here's some big capacitors, some smaller capacitors, all down here. There's ceramic. These are all leaded devices. A lot of times we use non-leaded devices now, surface mount, which have less inductance. These are coils of some sort, transformers, a toroid right there. So reactive components are basically components that have reactance, meaning an impedance, that is a frequency sensitive resistance. I like to express reactance that way, as a frequency sensitive resistance, meaning the resistance goes up or down with frequency depending on if it's a capacitive reactance or inductive reactance. So reactance is expressed in ohms, so it might as well be a resistance, but it's a frequency sensitive resistance. That's what reactance is. Its opposition to alternating current flow, although that's not 100% correct. Sometimes it supports it depending on how the component is configured in the circuit. We'll see that. So capacitors actually are short circuits to AC current, right? They get lower resistance, if you will, at the higher frequency. So it's inversely proportional. The reactance is inversely proportional to the value of the capacitance and the frequency. So here's the formula. XC, which is the capacitive reactance, is 1 over 2 pi FC. So if we have a 100 picofarad capacitor and 2 megahertz, you just plug and chug that number in there. 2 pi is 6.28. It's 2 megahertz. That's 100 picofarad. You get 796.2 ohms. So that's the equivalent resistor that capacitor is at that particular frequency. Notice that if you increase the frequency, since it's in the denominator, this is going to go down. So the higher the frequency, the lower the resistance or lower the reactance. So capacitors actually with leads, we have inductance, we have a little bit of resistance in there. So they're complex devices. We usually ignore everything except for the capacitor, except for at really high frequencies. Then all this stuff comes into play. Okay, and that's why surface mount capacitors are often used very small, no leads on them, which removes most of the inductance. Depending on the dielectric of the capacitor, we might have some leakage resistance though still. And obviously the more expensive capacitors have less leakage. So inductors are the opposite of capacitors. In other words, an AC signal going through an inductor will be tend to be stopped rather than let through as it is in a capacitor. It opposes current changes, so a series inductor is going to have a high resistance at high frequencies. An opposed low capacitor will have a low resistance at high frequencies. Okay, so they're expressed in millihenries or microhenries or nanohenries. Right, capacitors, you probably know, they're mostly microfarad. Most often we express those in microfarads. So the inductive reactance at X sub L is how we express the frequency-sensitive resistance of inductors. So here's some different kinds of inductors. This is a surface mount inductor down here. It's a toroid, like a donut. This here is a choke of some sort. It looks like a tunable core. Slide it in and out and it changes the inductance. And this is a ferrite bead. These are, you find these often on cords, external cords, to reduce electromagnetic interference coming out of, let's say, a CRT monitor or keyboard or something like that. This is a schematic symbol. PC board, you don't see this very often. This is a little inductor put on a PC board. So inductive reactance is 2 pi FL, not in the numerator, it's in the denominator. So this example is going to be 2 pi 6.28 times 18 megahertz times 40 microhenries. You get 4522 ohms. And again, as you increase the frequency, you're going to increase the reactance or the frequency-sensitive resistance. Now, resistors. Now, resistors aren't supposed to be reactive. Ideally, they are not. But if they have leads, any wire at all, whether it's coiled up or not, has inductance associated with it. So it ends up, and you know, it has some stray capacitance in there too, by the way. So in really high frequencies, you have to take that into account. So that's why we use a lot of surface mount parts. Tiny resistor chips used in surface mount circuits, they minimize the inductance and stray capacitance. So this is what it looks like in real life with high frequencies. Obviously at low frequencies, the capacitor becomes an open circuit, so it goes away. At low frequencies, The inductor, what does it do? It becomes a short circuit. It's just a wire. So they both go away and you end up with just a resistor. So one more thing, a skin effect, and this is, again, just with a wire, basically. As you ramp up the frequencies in wires, even coax cables and so on, for very high frequency, ultra high frequency, and microwave, what happens is the current tends to float towards the outside of the conductor rather than on the inside. And that's going to increase the, if all the electrons are flowing on just on the outside of the conductor, what happens is the resistance goes way up, right? Because you're not using the whole section of copper. Skin effect's a big deal if you have really high frequencies. So we do certain techniques, strip line techniques and things like that on circuit boards to minimize that. And here's a picture of all the electrons on the outside, no current flow on the inside. So very high resistance at high frequencies. Okay, let's look at tuned circuits. Tuned circuits, this is our lab this week, basically. We have a tuned circuit. And tuned circuits are made up of inductors and capacitors that resonate. All right, the resonant frequency is when the inductive reactance and the capacitive reactance are the same. All right, so there's some magical frequency, okay, that resonant frequency where both where the inductive reactance equals the capacitive reactance. That's the key, right? So a series resonant circuit is an inductor and a capacitor in series. This is the formula for it, 1 over 2 pi square root of LC. All right. So here's a schematic. Here's the L, there's the C, there's a resistor. I believe we do this in our lab, series RLC circuit. And notice here comes the capacitive reactance down this way. As frequency goes up, the reactance goes down. In other words, the resistance goes down. The inductor, however, increases in reactance, ohms, as you go up, and at one point they cross. And it is at that point that is the resonant frequency, that is the lowest resistance, if you will. It's the lowest impedance, more correctly, of this circuit is at resonance. So XL equals XC right here, and that's it. And you'll see that in your lab. Impedance of the circuit is, and you're going to need this a formula for your lab, R squared plus XL plus XC squared, square root, it's XL squared, at FR XL equals XC, so these two cancel out, right? So the total circuit is just the resistor. Square root of R squared is just R. So when XL squared, there should be XL squared, that's a mistake, minus XC squared, these cancel each other out, or they subtract out each other. So 1 over 2 pi square root of LC, resonant frequency of a 2.7 picofarad capacitor and 33 nanohenry inductor. Just plug it in, LC, square root, you end up with 533 megahertz. In other words, and again, this is another good example. You're going to want to keep your eye on this. Maybe write this one down. And keep all the formulas close by so you can use them. Resonant frequency, total circuit impedance is Z equals R, as we just said. Point at which a circuit impedance is lowest and a circuit current is the highest. Makes sense, right? Lower resistance, higher current. Current is in phase with the applied voltage at that point because it's resistive. At other points, the current and the voltage are not in phase. So above the resonant frequency, what happens? The inductive reactance is higher, the inductor's kicking in, right? Capacitive reactance basically shorts out. You can take that out, replace it with a wire. Circuit is inductive. Below the resonant frequency, it's capacitor. The capacitor is starting to show some resistance or reactance. The inductor's shorting out because it's getting closer to DC, right? So therefore, it's a capacitive circuit. Couple of terms here. Bandwidth of a series resonant circuit is a narrow frequency range over which the current is the highest. Half power points, 70%, right? 0.707 on either side. And the quality is basically the ratio of the inductive reactance to the total circuit resistance. So the higher the Q, okay, the lower the circuit resistance. Q, that's a good, it's quality. It's so ideal circuit would be infinite Q, right? No resistance. So at resonance, you've got zero resistance. Well, it's impossible. So you always have some winding resistance in the circuit from the inductor, if nothing else. And here's a graphic that shows the bandwidth, the 0.707. This is a current graph. So 70% off the peak is your half power points. And we've seen this before. Bandwidth is F2 minus F1. Here's another little exercise. You can do this on your own. Calculate the bandwidth, approximate resonant frequency in the Q based on these givens. And here's some little examples of Q and selectivity. Right now, this is lousy Q here. Look at how fat that is. It just really is wide. It's a little bit better. And the green one here is a narrow bandwidth, a very high Q circuit. So the more resistance you put in, the flatter this is going to be. Parallel resonant circuit is when you put inductor and capacitor in parallel, LCR or LC circuit. Resonance occurs, again, it's the same thing with inductor and capacitive reactances are equal. So we do one of these too, I think, in our lab. So here's the inductor capacitor in parallel, okay? So at resonance, the parallel tuned circuit appears to have infinite resistance and no current. So unlike the series resonant, where the series resonant circuit, where the circuit becomes a really low resistance, parallel resonant circuit, the circuit becomes real high resistance, okay? No current flows. So it has infinite impedance, acts as an open circuit. There's a high circulating current between the inductor and the capacitor, storing and transferring energy between them. That's why it's called a tank circuit, kind of tank that way, tank that way. It's like pouring water in and out of a tank. So this circuit here is called a tank circuit, all right, because the currents are flowing only between these two components. There's no longer any current through the whole circuit at resonance. Yeah, tank circuit, because a recirculating current is referred to as a tank current. So filters, we have all kinds of filters, passive filters and active filters. We're going to talk about low pass, high pass, band pass, and band reject filters. RC filters is a resistor and a capacitor. Low pass filters, we've looked at these before in other classes. I know you know this. So low pass filters are sometimes referred as high cut filters. I just call them low pass filters. Cutoff frequency is a point at which the resistance and the capacitive reactance are equal. So here's a low pass filter. It's low pass RC, passive filter. It's low pass because why? Well, the capacitor is going to short out high frequencies. So as you get higher in frequency, the output voltage goes down because this is shorting it out, right? So going along here at the mid-band, it's called mid-band gain or the pass band. And at some point when a capacitor starts to kick in at the minus 3 dB point, half power point, 0.707 of Vmax, that's the cutoff frequency, FCO. And for this example, it looks like it's about 600 hertz, okay? And we go down 20 dB per decade, so it means between 600 hertz and 6 kilohertz, which is a decade. You go down 20 dB, so it might be 6 dB per octave or 20 dB per decade. So that's what this is showing here. So there's 6 dB per octave. Okay, so that's at 1200 hertz. At 6 kilohertz, which is a decade, okay, you go down minus 3 to minus 23. So that's 20 dB per decade. Good diagram here. High-pass filter is the same exact circuit, but reverse the position of the capacitor and the resistor. Again, the formula is 1 over 2 pi RC. The formula for the high-pass filter was, for the low-pass filter was 1 over 2 pi RC. Easy to remember. You should commit this to memory. All right. If it's an inductor, it's R over 2 pi L. Write all these formulas down on one sheet of paper so you have them handy to do your homeworks and to do the exam with. It's a good idea. We also have notch filters or band stop filters. They're good for filtering out particular narrow ranges of frequency. Here's one. This is basically a high-pass filter coupled with a low-pass filter, and you get this little notch here. F notch is 1 over 2 pi RC. All these values are the same. That's a resistor, same resistor. That's that same resistor value divided by 2. These capacitors are equal. That's that same capacitor value times 2. And you get this nice notch filter here. You might ask yourself, what's the problem with this circuit? Well, it's not an active filter. It's a passive filter. You get loss, right? There is loss going through here, even in the pass band right over here, that you don't want. You know, you're going to get some loss through this filter because you get these voltage divider effects through these resistors. LC filters, inductors and capacitors, they're used with RF applications, and they can be, again, resonant. They are resonant circuits, and you've got a pass band with them, stop band, attenuation band. There is some insertion loss because of the inductor. Obviously, there's some lead inductance and things like that, but there's winding resistance. There's ripple in the pass band, meaning that the gain is not constant. And there's a shake factor, which is basically dependent on the Q. There's a poles and zeros. You've probably heard about these before. A pole is a frequency which there's a very high impedance in the circuit. A zero is where the impedance is very low. There's also a time delay, how long it takes for a signal to get through the circuit. That's a phase phenomenon. And then there's an attenuation rate or roll-off rate, which is really dependent on the number of poles of the circuit. Okay. So most of the time we develop these Butterworth and Chebyshev filters. These are named after people who design these particular filter topologies. There's a Cower and a Bessel. So the Butterworth filter is maximally flat in the pass band. I'll show you a diagram of this in a minute, but it's maximally flat. Uniform attenuation with frequency. Chebyshev's a little bit more aggressive, okay, but it's really ripply in the pass band. Same with this elliptical filter. The Bessel is a very important filter for RF because it has constant phase. Okay, and that's really important for passing square waves and things like that, as we'll see when we get to Fourier. So here's a diagram of them. Okay, here's the ripple in the pass band. So the Chebyshev is the orange. It's got lots of ripple. Elliptical has even more. But look at how aggressive their cutoff is, right? Butterworth, very flat in the pass band, and then gradually goes off. This is your typical 20 dB per decade thing. And the Bessel is pretty good too, but it's completely flat in the pass band. But again, the thing to remember about the Bessel is that it's linear phase, meaning different frequencies all have the same phase relationship. Really important. These other ones, you might have, let's say at 100 kilohertz have a 70 degrees phase, and at a megahertz you might have 110 degrees phase. Well, that messes up a square wave if you're trying to pass a square wave through the filter, and we'll see why in a minute. Don't see many mechanical filters. I made one when I was doing radar a long time ago for really high power applications. We're talking many kilowatts, where your regular inductors and capacitors wouldn't work. They're basically tubes with Teflon and discs in them. They look like pipes. Okay, most of the time they're bandpass filters. And here's some simple bandpass filters, LC bandpass filters. There's some examples in the textbook you're going to want to look at and homeworks on this. Just formulas. And there's band reject filters. We already looked at that. Band stop. These are the notch filters. You can do those with L's and C's too. Now, active filters, usually we make these out of op amps. The follow-on to our semiconductors class is integrated circuits, which is taught in the spring, and we do active filters in that. You can, unlike the passive filters that we've been looking at, you can add gain to them. There's no inductors. They're easy to tune, and you can provide isolation. So it's kind of a big deal. Variable state filter, we look at these in integrated circuits. You can do high pass, low pass, and band pass operation in one circuit. And you can make all those different filter topologies. You can make Butterworth and Chebyshev and Bessel and all those. Crystal and ceramic filters. Crystals basically are filters. They are, you've heard of crystals, those are frequency selective devices. Not too many ceramic filters these days. Don't see many of those around because crystals have become less expensive. This is what a crystal looks like in real life. I mean, a model. This is a model of a crystal. We have an R, L, S, C, and a parallel C. So it's a tuned circuit. But if you were to try to make a tuned circuit out of discrete inductors, capacitors, and resistors, you could never get the Q that you achieve out of a real crystal. And these are the schematic symbols for a crystal. This one here down at the bottom, this one up here, I'm not familiar with that one. I've never seen that. And I guess this is a ceramic filter. Again, I'm not too keen on ceramic filters. They're not used too much. We had a lab once a long time ago in this class where we used ceramic filters, but they're sort of obsolete now as far as I know. Surface acoustic wave was used in cell phones many years ago, analog cell phones. There was a company up in Lake Mary or Sanford called Sawtech. A friend of mine used to work at it, where they made their money building SAW filters for cell phones back in Nokia days. Not so much anymore. I think they're gone. Kind of interesting though. It's basically a piezoelectric ceramic, and these surface waves go from the input to the output. It's basically a little radio station. Okay, and they tune the distance between there so that only certain frequencies can get through. Very clever. I don't know that they're used anymore. Maybe. Switch capacitor filters, analog sample digital filters. We don't do any of this in this class, but just for sake of completeness, we present it. They are using, we're using FET switches here to switch capacitors on and off in a op-amp circuit here. We won't be studying this much. We do a little bit in integrated circuits maybe, but this circuit here would emulate this circuit here, this integrator. But I wouldn't worry too much about this. There's another one. So let's talk about Fourier theory, okay? The thing about Fourier theory is any non-sinusoidal waveform is made up of an infinite number of harmonically related sine waves, okay? So a square wave is a classic example of a non-sinusoidal wave, right? So here's a square wave. No, it's a sine wave, right? Well, actually, if you take all of these and combine them together, this is the first harmonic, second harmonic, third harmonic, fourth harmonic. If you take all the odd ones, in other words, first, third, fifth, seventh, ninth, all the way up to infinity, you make a square wave. Okay, you combine all those sine waves together. Okay, so here is a square wave, 50-50 duty cycle, and square wave is made up of a sine wave, a fundamental frequency of the square, plus an infinite number of odd harmonics. Okay. So what if you pass that square wave through a filter that is a low pass filter? What happens to the sine wave, to the square wave? Well, what's going to happen is all those higher order harmonics are going to be filtered out, and that square wave becomes what? A sine wave, because you filtered out all the high order harmonics. If you do, that's exactly what's going to happen. So 1 kilohertz square wave becomes a 1 kilohertz sine wave if you put a low pass filter on there that filters out everything above 1 kilohertz. You've got rid of the third, the fifth, the seventh, and everything all the way up. And that's pretty common to do. Turn square waves into sine waves. And we'll talk more about Fourier theory in class because it's important. So time domain versus frequency domain. Time domain is a scope, oscilloscope display. The frequency domain is a spectrum analyzer display, and that's what we're going to be looking at in the lab. We have spectrum analyzers in there. We'll be looking at some frequencies on that spectrum analyzer, and that's the frequency domain. Okay, so Fourier theory, we're going to see. All right, sorry for the interruption. Yeah, so frequency domain plots amplitude and variation with respect to frequency. That is what is on our spectrum analyzers. And a spectrum analyzer is basically a Fourier theory machine. It breaks the signal down into its frequency elements. So if you put a square wave into a spectrum analyzer, what you're going to see is the fundamental frequency, and you're going to see every odd harmonic. So if it's let's say it's a 100 kilohertz square wave, you're going to see 100 kilohertz, 300 kilohertz, 500, 700. Now, as you go up into the harmonics, the amplitude of those elements, of those components, reduces. Okay. So in other words, the main bang of the fundamental, which is like my example is 100 kilohertz, that's going to be the highest amplitude. And then as you go to 3 and 5, 7, they get smaller and smaller. So here's a little diagram. I'm not so sure about this one. This is the frequency domain. Yeah, so this is showing the time domain. This shows, if you notice, there's a lot of ripples on this square wave. This looks like it's becoming a sine wave. This is a bandwidth limited square wave because some of the higher order harmonics have been removed. So it's starting to morph into a sine wave. And this shows the fundamental and then the harmonics. And the frequency domain shows these spikes here. This is, again, what we'll see on our spectrum analyzer. What's this here? Okay, this is another expression. This is a full cosine wave. Don't worry too much about this, but this is the Fourier equation. Okay, don't have to worry about that too much. And as I was saying, the spectrum analyzer shows that. We're getting towards the end here. So, I think this is about it. If you have any questions, please do not hesitate to post something in the discussion section or bring it up in class. We'll be doing a little bit more of this, little review in class of this, especially the Fourier stuff when we do our lab. Okay? Thank you.